Hello aspirants, welcome to Magic World of Physics. In this video, we're going to discuss about some questions from classical mechanics part which is asked in various exams like GATE, Barc, Just, Differ. Hope this video will be helpful for your coming Barc exam 2026. Without any further delay, let's get started. Question is, the Poisson bracket R, P has the value dash. So the solution is, we know r is equal to x I cap plus y j cap plus z k cap, and the mode r is square root over x square plus y square plus z square. P is equal to px I cap plus py j cap plus pz k cap, and mode p is equal to square root over px square plus py square plus pz square. Then the Poisson bracket of r comma p is equal to dou r by dou x into dou p by dou px minus dou r by dou px into dou p by dou x plus dou r by dou y into dou p by dou y minus dou r by dou py into dou p by dou y plus dou r by dou z into dou p by dou pz minus dou r by dou pz into dou p by dou z. This is equation number 1. Here the variables are x, px, py, y, z, pz. So here we can differentiate r with respect to x, that is dou r by dou z dou x is equal to 1 by 2 into 2x by square root over x square plus y square plus z square, that is equal to x by r. This is equation number 2. Similarly, we can find dou r by dou y and dou r by dou z, that is dou r by dou y is equal to y by r and dou r by dou z is equal to z by r. These are equation number 3 and 4. Substituting 2, 3, 4 in 1, we get r comma p is equal to xpx by rp plus ypy by rp plus zpz by rp. This is equal to r dot p by rp, that is r cap dot p cap. So the answer is r cap dot p cap. The next question is, let a comma b comma c are the functions of the phase space variables, the coordinates and the momenta of the mechanical system. If the curly bracket represents the Poisson bracket, then the value of a comma b comma c minus a comma b comma c is given by dash. We know by Jacobi identity we can write the Poisson bracket as a comma b comma c plus b comma c comma a plus c comma b a comma b is equal to 0. That is the Poisson bracket of a comma, the Poisson bracket of b comma c plus c comma a comma b is equal to minus b comma c comma a. This is equation number 1. And we know that a comma b is equal to minus b comma a. This is equation number 2. Substituting 2 in 1, we get a comma b comma c minus a comma b comma c is equal to c comma a comma b. So the answer is c comma a comma b. So the next question is, the coordinates and the momenta x comma p of a particle satisfy the canonical Poisson bracket relation x comma p is equal to Kronecker delta ij if c1 is equal to x2 p3 plus x3 p2 and c2 is equal to x1 p2 minus x2 p1 are the constant of motion, and if c3 is equal to c1 comma c2 which is equal to x1 p3 plus x3 p1, then we need to check which option is correct. Here we know that x1 p1, x2 p2, x3 p3 are the variables. So the Poisson bracket of c2 comma c3 can be expanded like this, that is c2 comma c3 is equal to dou c2 by dou x1 into dou c3 by dou p1 minus dou c2 by dou p1 into dou c3 by dou x1 plus dou c2 by dou x2 into dou c3 by dou p2 minus dou c2 by dou p2 into dou c3 by dou x2 plus dou c2 by dou x3 into dou c3 by dou p3 minus dou c2 by dou p3 into dou c3 by dou x3, which is equal to p2 into x3 plus x2 dot p3 plus minus p1 into 0 minus 0 plus 0, which is equal to p2 x3 plus x2 p3. And from the question itself given, it is c1, that is c2 comma c3 is c1. Then we need to check c3 comma c1. So this also can be expanded as dou C3 by dou X1 into dou C1 by dou P1 minus dou C3 by dou P1 into dou C1 by dou X1 plus dou C3 by dou X2 into dou C1 by dou P2 minus dou C3 by dou P2 into dou C1 by dou X2 plus dou C3 by dou X3 into dou C1 by dou P3 minus dou C3 by dou P3 into dou C1 by dou X3, which is equal to P3 into 0 minus X3 into 0 plus 0 into X3 minus 0 into P3 plus P1 into X2 minus P1 into P2 into X1, which is equal to minus of X1 P2 minus X2 P1, which is equal to minus C2. We can say the Poisson bracket of C2 comma C3 is equal to C1 and the Poisson bracket of C3 comma C1 is equal to minus C2. The next question is the Hamiltonian of a simple pendulum consisting of a mass m attached to a massless string of length L is H is equal to P theta square by 2 ml square plus mgl into 1 minus cos theta. If L denotes the Lagrangian, then the value of dl by dt is dash. So here we need to find dl by dt. So dl by dt is equal to L comma h plus dou L by dou t. And here h is given, that is p theta square by 2 ml square plus mgl into 1 minus cos theta. We know that L is equal to pi qi dot minus h. Here the generalized coordinate is theta. So we can write it as p theta theta dot minus h. And we know theta dot is dou h by dou p theta, that is p theta by ml square. So substituting all these values in the equation of L, we can rewrite it as L is equal to ml square theta dot square by 2 minus mgl into 1 minus cos theta. And if we substitute the value of theta dot in this equation, we can rewrite it as L is equal to p theta square by 2 ml square minus mgl into 1 minus cos theta. Then from here we have understood the value of L. We need to find the Poisson bracket of L comma h, that is dou L by dou theta into dou h by dou p theta minus dou L by dou p theta into dou h by dou theta. If we solve this, we get it as minus 2g by L into p theta sin theta. And we know dou L by dou t is equal to 0. Then we can write dl by dt as minus 2g by L p theta sin theta. The answer is minus 2g by L p theta sin theta. So the next question is a particle moves in one dimension, the potential V is equal to half k x square, where k is a time dependent parameter, then d by dt of V, that is the rate of change of expectation value of the potential energy, is dash. So here we need to find the rate of change of the expectation value of that potential V. So the solution is, here we know V is equal to half k x square. So h is equal to p square 2m plus half k x square. Then d by dt of V is equal to 1 by h cut 2i into the Poisson bracket of V comma h plus dou V by dou t is equal to 1 by I h cut into expectation value of the Poisson bracket of 1 by 2 k x square comma p square by 2m plus half k x square, because here we have substituted the value of V and h. Now dou V by dou t is equal to x square by 2 into dou k by dou t, because k is a time dependent parameter. Can be rewritten as 1 by I h cut into the Poisson bracket of half k x square comma half k x square plus the Poisson bracket of half k x square comma p square by 2m plus the expectation value of x square by 2 into dou k by dou t. This is equal to 1 by I h cut into k by 4m, the expectation value of the Poisson bracket of x square comma p square plus half expectation value of x square into dou k by dou t. The Poisson bracket of x square comma p square is equal to the Poisson bracket of x into x comma p square, which is equal to x into Poisson bracket of x comma p square plus x comma p square into x, which is equal to x into the Poisson bracket of x comma p plus the Poisson bracket of x comma p into p plus p into the Poisson bracket of x comma p into x plus the Poisson bracket of x comma p into x, which is equal to x into p into x comma p plus Poisson bracket of x comma p into p plus p into the Poisson bracket of x comma p into x plus the Poisson bracket of x comma p into x. This is equal to x into p into I h cut, because x comma p, the Poisson bracket of x comma p is equal to I h cut. So we can rewrite it as x into p into I h cut plus I h cut p in plus p into I h cut x plus I h cut x. This is equal to x into 2 ih cut p plus p into 2 ih cut x. This is equal to 2 ih cut into xp plus px. Thus the Poisson bracket of x square comma p square is equal to 2 ih cut xp plus px. Therefore, d by dt of the Poisson, d by dt of this average value v is equal to k by ih cut 4m into 2 ih cut into xp plus px plus half into x square dk by dt. That is equal to, taking 2 outside, we can write 2k by 4m value of xp plus px plus half dk by dt expectation value of x square. This is equal to k by 2m into the expectation value of xp plus px plus half dk by dt expectation value of x square. So this is a solution. The next question is, a particle in 2 dimension is in a potential v is equal to x plus 2x. Which of the following is a constant of motion? This can be solved in two methods, because we know that the first method is, we know that if there is a constant of motion, the Poisson bracket of that constant of motion with h, that is the Hamiltonian, is 0. So this, in this way we can also solve it. That is, we know that h is equal to px square by 2m plus py square by 2m plus x plus 2y, because v is equal to x plus 2y here. Then we take an option from this option. Let's say we have taken the option A. If this is a constant of motion, the Poisson bracket of this C along with h will give the answer. So we know that the Poisson bracket of C comma h is equal to dou cx into dou h by dou px minus dou c by dou px into dou h by dou x plus dou c by dou y into dou h by dou py minus dou c by dou py into dou h by dou y. We have taken the option A, that is py minus 2px is taken as c. That is the constant. If it is a constant of motion, then we need to check the Poisson bracket of that constant with h. That is dou c by dou x is equal to 0, dou c by dou y is equal to 0, dou c by dou px is equal to minus 2, dou c by dou py is equal to 1, dou h by dou x is equal to 1, h by dou y is equal to 2, dou h by dou px is equal to px by m, dou h by dou py is equal to py by m. So we can write the Poisson bracket of py minus 2px comma h is equal to 0. This means that this is the constant of motion, because if we have taken the Poisson bracket of this constant of motion with h, we get the answer as 0. Here we get the answer as 0. So A is the answer. This is the one method of solving this. The another method is using the Hamilton equation. That is, we know px dot is equal to minus dou h by dou x. That is minus dou by dou x of px square by 2m plus py square by 2m plus x plus 2y. That is equal to minus 1. Then py dot is equal to minus dou h by dou y. That is equal to minus dou by dou y of px square by 2m plus py square by 2m plus x plus 2y. That is equal to minus 2. So here we get px dot is equal to minus 1 and py dot is equal to minus 2. That is py dot is equal to 2px dot. That is py dot minus 2px dot is equal to 0. That is dpy by dt minus 2p dp x by dt is equal to 0. That is dy dt of py minus 2px is equal to 0. That means py minus 2px is equal to a constant. So in this method also we can solve this question. Next question is, the Hamiltonian of a classical one-dimensional harmonic oscillator is h is equal to half into p square plus x square in suitable units. Then the total time derivative of the dynamic variable p plus root 2x is dash. Here it is not given that f is explicitly depends upon the time. So we have taken that dou f by dou t is 0. Here f means the function. Let it be a. We can take any variable. So if here we have taken the function as a. Given h is equal to p square by 2 plus x square by 2, and we have taken the p plus root 2x as a, and we know dA by dt is equal to Poisson bracket of a comma h plus dou a by dou t. Here it is not given that a is depending. A means that function is not depending upon the time. It is not mentioned here, so we have taken dou a by dou t is equal to 0, because it is not mentioned that it depends upon time. So we consider that it is doesn't depending upon time, so that is dou a by dou t is equal to 0. That is dA by dt is equal to Poisson bracket of a comma h. That is dA by dt is equal to Poisson bracket of p plus root 2x comma p square by 2 plus x square by 2. That is equal to Poisson bracket of p comma x square by 2 plus Poisson bracket of root 2x comma p square by 2, which is equal to minus 2x by 2 plus root 2 into 2p by 2, because we know that the Poisson bracket of p comma p square is equal to 0 and x comma x square is equal to 0. So this can be solved like this. That is equal to minus x plus root 2p, which is equal to root 2p minus x. So the next question is, a system is governed by the Hamiltonian h is equal to half into px minus ay the whole square plus half into py minus bx the whole square, where a and b are constant, px, py are the momenta conjugate to x and y respectively. For what values of a and b will the quantities px, 3y and py plus 2x be conserved? So here we need to check if this py plus 2x and px minus 3y is to be a constant of motion, then what should be the value of a and b? That means we should have taken the Poisson bracket of this function with Hamiltonian, and check if we want to make it 0, what will be the value of a and b. So that if you have taken the Poisson bracket of a function with h, that is Poisson bracket of f comma h is equal to dou f by dou x into dou h by dou px minus dou f by dou px into dou h by dou x plus dou f by dou y into dou h by dou py minus dou f by dou py into dou h by dou y. So we here f is equal to px minus 3y. So we need to find dou h by dou px, that is equal to half into 2 into px minus ay into 1, that is equal to px minus ay. Then dou h by dou py is equal to half into 2 into py minus bx, which is equal to py minus bx. Then dou h by dou x is equal to half into 2 into py minus bx into minus b, that is equal to minus b into py minus bx. Dou h by dou y is equal to half into 2 into px minus ay into minus a, that is equal to minus a into px minus ay. So we can write px comma 3y comma h is equal to 0 minus 1 into minus b into py minus bx plus minus 3 into py minus bx minus 0 is equal to 0. That is equal to b into py minus bx minus 3 into py minus bx is equal to 0. That is b minus 3 into py minus bx is equal to 0. So if we want to make that equation equal to 0, here the b value should be 3. So that b is equal to 3. Then the Poisson bracket of py plus 2x comma h is equal to the Poisson bracket of 2 into px minus ay minus 0 into 0 plus 0 minus 1 into minus a into px minus ay, that is 2 into px minus ay plus a into px minus ay equal to 0. So if it would be 0, then a plus 2 is equal to 0. That means a should be minus 2. So the value of a is minus 2 and b is equal to 3. The next question is, the Lagrangian of a system moving in 3 dimensions is L is equal to half m x1 dot square plus m x2 dot square plus x3 dot square minus half k x1 square minus half k x2 plus x3 the whole square. The independent constant of motion is or r dash. So here we need to find the constant of motions. So for simplicity, we have taken x1 comma x2 comma x3 as x comma y comma z. We know L is equal to half m x dot square plus m into y dot square plus z dot square minus half k x square minus half k y plus z the whole square. That is px dot is equal to dou L by dou x, that is not equal to 0. That similarly py dot not equal to 0, pz dot not equal to 0. That means the linear momentum is not conserved. If it should be conserved, then px dot should be 0. That then only px become constant. So here linear momentum is not conserved. Then similarly px is equal to we know dou L by dou x dot, that is equal to half into m into 2 into x dot, that is equal to mx dot. That means px is equal to mx dot, that is x dot is equal to px by m. Similarly y dot is equal to py by 2m and z dot is equal to pz by 2m. Then h is equal to x dot px plus y dot py plus z dot pz minus L. This is equal to px square by m plus py square by 2m plus pz square by 2m minus m into px square by 2m square minus py square by 4m minus pz square by 4m plus half kx square plus half ky plus z the whole square. This is equal to px square by 2m plus py square by 4m plus pz square by 4m plus half kx square plus half ky plus z the whole square. We know dou h by dou t is equal to 0. That means h is conserved here. That means if h is conserved here, so we can say that this Hamiltonian is the energy. So that means energy is conserved here. Then we know Lx is equal to ypz minus zpy, that is dlx by dt is equal to Lx comma h plus dou Lx by dou t. Then Lx comma h is equal to ypz minus zpy comma h. Then that is a Poisson bracket of y comma h into pz plus y comma y into pz comma h minus z comma h into py minus z into py comma h, which is equal to Poisson bracket of y comma py square by 4m into pz plus y Poisson bracket of pz comma half k y plus z the whole square minus is Poisson bracket of z comma pz square by 4m into py minus z Poisson bracket of py comma half k y plus z the whole square, that is equal to 2 py pz by 4m plus y into 0 minus half k square. This is not square, this is into 2. So this can be written as 2 py pz by 4m plus y into 0 minus half into k into 2 into y plus z minus 2 py pz by 4m minus z into 0 minus half into k into 2 into y plus z, that is minus k into y square plus yz plus k into z square by yz, which is equal to minus k into y square minus z square. This is equal to k into z square minus y square. That means dlx by dt not equal to 0. Similarly, dly by dt not equal to 0 and dlz by dt not equal to 0. That means angular momentum is also not conserved. So the only term conserved here is the energy. So energy is the only term that is conserved here. So the option is A. So the next question is, the Hamiltonian of a system with 2 degrees of freedom is h is equal to q1 p1 minus q2 p2 plus a q1 square, where a greater than 0 is a constant. The function q1 q2 plus lambda p1 p2 is a constant of motion only if lambda is dash. So here we need to find the value of lambda. So h is equal to q1 p1 minus q2 p2 plus a q1 square, and here f is equal to q1 q2 plus lambda p1 p2. Then df by dt is equal to Poisson bracket of f comma h plus dou f by dou t. Dou f by dou t is equal to 0 here. Then df by dt is equal to f comma h, that is equal to 0. Then f comma h is equal to dou f by dou q1 into dou h by dou p1 minus dou f by dou p1 into dou h by dou q1 plus dou f by dou q2 into dou h by dou p2 minus dou f by dou p2 into dou h by dou q2 is equal to 0. Because here it is mentioned that f is a constant of motion, so that the Poisson bracket of f comma h is 0. So it can be solved as q1 into q2 minus lambda p2 into p1 plus 2a q1 plus q2 into minus q2 minus lambda p1 into minus p2 is equal to 0. That is q2 q1 minus lambda p1 p2 minus 2a lambda p2 q1 p2 minus q1 q2 plus lambda p1 q2 is equal to 0. So equation is satisfied only if lambda equal to 0. So the value of lambda is 0.
So the next question is, let Q and P be the canonical coordinate and momentum of a dynamical system. Which of the following is a canonical transformation? So if we need to check the which option is the canonical transformation.
If it is a canonical transformation, then the Poisson bracket will be 1. So we need to check if we get the answer as 1 or not. For A, Q1 is equal to Q square by root 2, comma P1 is equal to P square by root 2. Then the Poisson bracket of Q1 comma P1 is equal to dou Q1 by dou Q into dou P1 by dou P minus dou Q1 by dou P into dou P1 by dou Q. This is not equal to 1. That means this is not a canonical transformation. So let's check for B. For B, Q2 is equal to 1 by root 2 into P plus Q and P2 is equal to 1 by root 2 into P minus Q. So if we take in the Poisson bracket of Q2 comma P2, we get it as 1. That means it is a canonical transformation. So the correct answer is option D. So because only 2 is the right answer. So the option D is the answer. The next question is, let X denote the position operator and P the canonically conjugate momentum operator of a particle. Then the commutator 1 by 2m p square plus beta x square, comma 1 by m p square by gamma x square, where beta and gamma are constant, is 0 if. Here we need to check if this commutator value becomes 0, then what will be the relationship between this gamma and beta. That is the commutator of 1 by 2m into p square plus beta x square, comma 1 by m p square plus gamma x square should be 0. That is 1 by 2m gamma p square comma x square plus beta by m x square comma p square is equal to 0. That is minus gamma by 2m into x square comma p square. Here the negative comes because we know that p square comma x square is equal to minus x square comma p square. So that here the minus comes. Then this plus beta by m into x square plus p square. This is equal to 0. That means 1 by m into commutator of x square comma p square into minus gamma by 2 plus beta is equal to 0. That means gamma is equal to 2 beta. So the relationship between this gamma and beta is gamma is equal to 2 beta. So the next question is, a Hamiltonian system is described by the canonical coordinate q and canonical momentum p. A new coordinate q is defined as q is equal to small q t plus tau plus p t plus tau, where t is the time and tau is a constant. That is, the new coordinate is a combination of old coordinate and momentum at a shifted time. The new canonical momentum p of t can be expressed as dash. Here small q comma p as the old coordinates and the new coordinates are capital Q and capital P, and here it is given that capital Q is equal to small q plus p, and we need to check the capital P value so that the value of the Poisson bracket become 1. So we need to check for each option. So for option A, we need to check q comma p, that is equal to q plus p comma p minus q. This is equal to the Poisson bracket of q comma p minus q into q comma q plus Poisson bracket of p comma minus q plus Poisson bracket of p comma p. That is equal to 2. It's not a canonical transformation. Then option B, q comma p is equal to of q plus p comma p minus q. This become equal to 2. This is also not a canonical transformation. Then coming to option C, that is q comma p is equal to half into q plus p comma p minus q. This has become equal to 2 by 2, that is equal to 1. This is a canonical transformation. Then option D, that is q comma p is equal to 1 by 2 into q plus p comma p minus q. That become equal to 2 by 2. This is equal to 1. Means here C and D option gives the value 1. We can't say that both are canonical transformation because and the Poisson bracket value become equal to 1. To become a canonical transformation, we need to satisfy one more condition. The canonical transformation should obey the translational symmetry. Translation symmetry means these two should be taken at the same time. The C option, if you observe, we see the time as t minus tau and t plus tau. That means the translation symmetry doesn't exist because it is taken at different times. So
there doesn't exist the translational symmetry. Even if that portion bracket value is 1, as it is not obeying the translation symmetry, we can't say that it is a canonical transformation. So the option C is wrong. But coming to option D, here the it is measured at equal time, that is t plus 2, and here the portion bracket is also 1, so that we can say the option D is the most appropriate answer.
The next question is, a canonical transformation relates the old coordinates to the new ones by the relation q is equal to q square plus p and p is equal to p by 2q. The corresponding time independent generating function is dash. So here it is given capital Q as small q square and capital P as small p by 2q. That is small p is equal to 2q capital P. So if you observe the capital Q and small p, these two equation, we understood that this is the generating function of F2 type. So we can write dou F2 by dou Q is equal to P, that is dou F2 by dou Q is equal to capital P into 2Q. That is integrating this equation, we get F2 is equal to Q square P plus F of P. Then we know dou F2 by dou P is equal to capital Q, this is equal to Q square. Integrating this, we get F2 is equal to Q square P plus F of Q. Comparing both sides, we get F of Q is equal to F of P, which is equal to 0. That means F2 is equal to Q square capital P. Then the next question is, a mechanical system is described by the Hamiltonian H is equal to P square by 2m plus half m omega square Q square as a result of the canonical transformation generated by F is equal to minus Q by Q. The Hamiltonian in the new coordinates Q and the momentum P becomes dash. H is equal to P square by 2m plus half m omega square Q square. Here F is equal to minus Q by Q. So we can say that here F is a function of capital Q and small q. So this is generating function F1 type. So we can write dou F1 by dou Q is equal to P, that is Q by Q square is equal to P. Dou F1 by dou capital Q is equal to minus capital P, that is equal to minus 1 by Q is equal to minus capital P, that is Q is equal to 1 by P. And from these two equations 1 and 2, we can write small p is equal to q p square, that is small q is equal to because we have written small p is equal to q p square because we know that small q is equal to 1 by capital P. So substituting all these values in the value of H Hamiltonian, we can write Hamiltonian as H is equal to P square by 2m plus half m omega square Q square is equal to Q square P raised to 4 by 2m plus half m omega square into 1 by P square, which is equal to 1 by 2m Q square P raised to 4 plus 1 by 2 m omega square raised to minus 2. So the next question is, a canonical transformation is made through the generating function f is equal to q square p on the Hamiltonian H is equal to p square by 2 alpha q square plus beta by 4 q raised to 4, where alpha and beta are constant and the equations of motions are dash. Here H is equal to f is equal to q square p, so this is an f2 type generating function. Then dou f2 by dou q is equal to p and dou f2 by dou p is equal to capital Q. Here it is given H is equal to P square by 2 alpha Q square plus beta by 4 Q raised to 4. And by solving dou F2 by dou Q is equal to P, we get P is equal to 2QP and capital Q is equal to Q square. That implies Q is equal to capital Q the whole raised to 1 by 2 and P is equal to 2Q the whole raised to 1 by 2 into capital P. Then H is equal to 4q p square by 2 alpha q plus beta by 4q square, which is equal to 2p square by alpha plus beta q square by 4. Then the Hamilton equations, dou h by dou p is equal to q dot, that is equal to q dot is equal to 4p by alpha, and dou h by dou q is equal to minus p dot, that is p dot is equal to minus beta q by 2. These are the Hamilton equations of motion. So, and then moving to the next question, then that is a canonical transformation is performed on the Hamiltonian H is equal to P square by 2m plus half m omega square Q square via the generating function f is equal to 1 by 2 m omega Q square cot
q. If q of 0 is equal to 0, which of the following graph show the schematically the dependence of q on t? So here we need to find the dependence of q on t, and we need to find the graph that shows this dependence. Here f is equal to m omega q square by 2 cot q. So we can say that f is depending upon q and capital Q. So this is an f1 type function. That is f1 is equal to m omega q square by 2 cot q. Then k is equal to h plus dou f1 by dou t. That is equal to h plus 0. This is equal to p square by 2m plus half m omega square q square. Then dou f1 by dou q is equal to p. That is minus dou f1 by dou q is equal to capital P. Then p is equal to m omega q cot q. The equation dou f1 by dou q, we can write p is equal to m omega q cot q, and from minus dou f1 by dou q is equal to capital P, we can write m omega q square by 2 cosec square q is equal to capital P, that is small q is equal to square root over 2 capital P by m omega sin q. So that is small p is equal to m omega. Substituting the value of q in this small p, we get small p is equal to m omega square root over 2 capital P by m omega sin q cot q. That is small p is equal to square root over 2 capital P m omega cos q. That is k is equal to 2p m omega cos square q by 2m plus half m omega square 2p by m omega sin square q. That is equal to m omega cos square q plus p omega cos square q plus p omega sin square q. That is equal to p omega. That is we can write the k is equal to p omega. Then q dot is equal to dou k by dou p. That is equal to omega. That is q dot is equal to omega means dq by dt is equal to omega. Integrating this, we get q is equal to omega t plus c1. So this equation represents the straight line curve. So we can say that from the dependence of q on t, we can say the graph is straight line. So the next question is, the generator of the infinitesimal canonical transformation q gives q dash which is equal to 1 plus epsilon q, and p changes to p dash which is equal to 1 minus epsilon p is dash. Here it is given that after the canonical transformation q changes to q dash and p changes to p dash, and we assume that the q dash means it is mentioned that it is an infinitesimal change. That means q dash is equal to q plus delta q. So we know that here it is mentioned q dash is equal to 1 plus epsilon into q, and we know q dash is equal to q plus delta q. So it can be written as q plus delta q is equal to q plus q epsilon. That is delta q is equal to q epsilon. Similarly, we can write p dash also. That is p dash is equal to 1 minus epsilon into p. That is p dash is equal to p plus delta p, which is equal to 1 minus epsilon into p. Then p plus delta p is equal to p minus epsilon p. That is delta p is equal to minus epsilon p. And we know that delta q is equal to dou g by dou p, and delta p is equal to minus dou g by dou q, where g is the generator. So substituting these into this equation, we can rewrite it as dou g by dou p is equal to q epsilon, and minus dou g by dou q is equal to minus epsilon p. That is dou g by dou q is equal to epsilon p. Integrating this, we get g is equal to epsilon pq plus f of p. Then dg by dp is equal to epsilon q plus df by dp. And we know dg by dp is also q epsilon. So that we can write epsilon minus q epsilon, which is equal to df by dp. That is q epsilon minus q epsilon is 0. That means df by dp is 0. That is f of p is a constant. Similarly, we can solve dou g by dou p is equal to q epsilon also, because here if we solve this by integrating, we get g is equal to integrate of epsilon q dp. That is g is equal to epsilon qp plus f of q, that is dou g by dou q is equal to epsilon p plus df by dq, that is substituting the value of dg by dq as epsilon p, we can solve this as df by dq is equal to 0. That means f of q is a constant. So from here we can write that we know that f of p and f of q is a constant. That means the generator function is epsilon qp. So that the answer is, here the epsilon is a constant, so that we can say that the answer is option B, that is qp. Next question is, a particle of unit mass in a potential V is equal to ax square plus b by x square, where a and b are positive constants. The angular frequency of small oscillation about the minimum of the potential is dash. So here V is equal to ax square plus b by x square. Then to find the equilibrium point, we differentiate it. That is dou v by dou x is equal to 0. That is 2ax minus 2b by x cube is equal to 0. That is a x raised to 4 minus b is equal to 0. That is x0 is equal to b by a the whole raised to 1 by 4. And we know that omega is equal to square root over k by m and m is equal to 1. And k is equal to dou square v by dou x square at x is equal to x naught. And we know that dou square v by dou x square is equal to 2a plus 6b by x naught the whole raised to 4. That is equal to, substituting the value of x naught here, we get 2a plus 6b by b by a, which is equal to 8a. So from here we need to find the value of omega, that is omega is equal to square root over k by m. M is equal to 1, so that omega is equal to square root over 8a. Next question is, the potential of a diatomic molecule as a function of distance r between the atoms is V is equal to minus a by r raised to 6 plus b by r raised to 12. The value of the potential at equilibrium separation between the atoms is dash. So here it is given that V is equal to minus a by r raised to 6 plus b by r raised to 12. Then to find the equilibrium separation, we know dv by dr, that is equal to 6a by r raised to 7 minus 12b by r raised to 13, which is equal to 0. That is 6 by r raised to 7 into a minus 2b by r raised to 6 is equal to 0. So that 6 by r raised to 7 is equal to 0, and can also a minus 2b by r raised to 6 is equal to 0. So that a is equal to 2b by r raised to 6, that is r raised to 6 is equal to 2b by a, that is r is equal to 2b by a the whole raised to 1 by 6, which can be written as r naught. So this is the equilibrium separation between the diatomic molecules. Here we need to find out the value of V at this equilibrium separation, that is V of 2b by a the whole raised to 1 by 6, and this is equal to minus a by 2b by a plus b by 2b by a the whole square, that is equal to minus a square by 2b plus b a square by 4b square, which is equal to minus a square by 2b plus a square by 4b, which is equal to a square into 1 by 4b minus 1 by 2b, which is equal to a square into 2b minus 4b by 8b square. This is equal to minus a square into 2b by 8b square, which is equal to minus a square by 4b, which is equal to v minimum. So this is the value of the potential at the equilibrium separation. The next question is, consider the motion of a classical particle in one-dimensional double-well potential V is equal to 1 by 4 into x square minus 2 the whole square. If the particle is displaced infinitesimally from the minimum on the x-axis, then we need to find which option is right. So here we have given the value of potential, and first we need to draw the graph of potential with respect to this equation. So here we have given V is equal to 1 by 4 into x square minus 2 the whole square. So that dou V by dou x is equal to 1 by 4 into 2 into x square minus 2 into 2x, that is x into x square minus 2. If we equate the value to 0, that is dou V by dou x is equal to 0, we get the equilibrium separation. So that the equilibrium separation is x is equal to 0 and x is equal to plus or minus root 2. We can find dou square V by dou x square, that is equal to 3x square minus 2. Then dou square V by dou x square at x is equal to 0 is minus 2. So this is maxima. So this shows the unstable equilibrium point, that is UEP. And here dou square V by dou x square at x is equal to plus or minus root 2 is equal to 4. So this is minima. So this is an stable equilibrium point. So here we get the and unstable equilibrium points. Now we can draw the graph of V. So here we get a right well and left well, because in the question itself it is mentioned that we get a double well. Here we understood that x is equal to plus or minus 2 is the UEP points, and this x is equal to plus or minus 2 is the SEP points. X is equal to 0 is the UEP point. And here an energy E is marked, and the turning points are x1, x2, x3, x4. Here it is understood that from x3 to x4 it is the classically allowed region, and also from x1 to x2 it is classically allowed region, but from x4 to x1 it is classically forbidden region. Then coming to the options. Option C says that the particle will switch between right and left wells. But this is wrong, because a classical particle cannot switch between the classically allowed and the classically forbidden region. Only quantum particle can penetrate through the region, that is the quantum tunneling. So that here it is a classical particle, so this is not possible to switch between the right well and left well. So we can say that the option C is wrong. Now we need to check about the option A and option B. For that we need to find omega, that is the angular frequency. We know omega is equal to square root over k by m. K is the dou square v by dou x square at x is equal to x naught, and x naught is the stable equilibrium point. So here the value of k at regarding the SCP point is 4. So that omega is equal to square root over 4 by m, that is equal to 2 by root m. Here in this question it is not mentioned the value of m, that is the mass. So if we take the value of m as 1, we get the omega as 2. And if we take the value of m as 2, then omega is equal to square root over 2. So both options can be possible, that is option A and option B is right, because it executes the SHM in the right well and left well. But in the option it is only mentioned about the right well, but the option A and option B is right, because it is not mentioned the value of m. If it is mentioned that the value of m is 1, then omega is equal to 2. Then only B option is right. Then coming to the option D. Option D is not right, because it will be right only if the frictional force or the system should be dissipative, but here the system is conservative. The option D says that the particle will approach the bottom of the right well and settle there. This is not possible, as here the system is conservative. This is possible only if we consider this system as a dissipative one. Means if that system present there, if there is a presence of the frictional force in the system, we can say that the option D can be right. But here the system is conservative, so that the option D is wrong. So the option A and option B is right.
Next question is, a particle of mass m is moving in the potential V of x is equal to minus 1 by 2 ax square plus 1 by 4 bx raised to 4, where a and b are positive constants. The frequency of small oscillation about the point of stable equilibrium point is dash. Here is equal to minus 1 by 2 ax square plus 1 by 4 bx raised to 4. Dou v by dou x is equal to 0, that is minus ax plus bx cube is equal to 0, that is x into minus a plus bx square is equal to 0. That is, solving this we get x is equal to plus or minus a by b the whole raised to 1 by 2 and x is equal to 0. Dou square v by dou x square is equal to minus a plus 3 bx square. At x is equal to 0, dou square v by dou x square is equal to minus a. It is negative, so this is the stable point. Dou square v by dou x square at x is equal to plus or minus a by b the whole raised to 1 by 2, which is equal to minus a plus 3b into a by b, which is equal to 2a. This is positive, so this is a stable point. Omega, this is equal to square root over dou square v by dou x square by m. This is equal to square root over 2a by m. So that the answer is square root over 2a by m. The next question is, a particle of mass m moves in the one-dimensional potential V is equal to alpha by 3x cube plus beta by 4x raised to 4, where alpha, beta greater than 0. One of the equilibrium points is x is equal to 0. The angular frequency of small oscillation about the other equilibrium point is dash. Then V is equal to alpha by 3x cube plus beta by 4x raised to 4. dV by dx is equal to alpha by 3 into 3x square plus beta by 4 into 4x cube, which is equal to alpha x square plus beta x cube. This is equal to x square into alpha plus beta x, which is equal to 0. That is, x square is equal to 0, that is x is equal to 0, and alpha plus beta x is equal to 0, that is alpha is equal to minus beta x, that is x is equal to minus alpha by beta. d square v by dx square is equal to alpha into 2x plus beta into 3x square, that is equal to 2x alpha plus 3 beta x square. Dou square v by dou x square at x is equal to 0 is equal to 0. Dou square v by dou x square at x is equal to minus alpha by beta is equal to 2 into minus alpha by beta into alpha plus 3 beta into minus alpha by beta the whole square, which is equal to minus 2 alpha square by beta plus 3 alpha square by beta. This is equal to alpha square by beta. So this is a stable equilibrium point. K is equal to d square v by dx square at x is equal to x naught, that is equal to alpha square by beta. Then omega is equal to square root over k by m. This is equal to square root over alpha square by m beta. This is equal to alpha by square root over m beta. So the next question is, a particle of mass m kept in the potential V is equal to minus 1 by 2 kx square plus 1 by 4 into lambda x raised to 4, where k and lambda are positive constants, undergoes small oscillation about an equilibrium point. The frequency of oscillation is dash. So here V is equal to minus half into kx square plus 1 by 4 into lambda x raised to 4. So dV by dx is equal to 0, that is equal to minus kx plus lambda x cube is equal to 0. So that x is equal to 0 and x square is equal to k by lambda, that is x is equal to square root over k by lambda. So this can be written as x naught. Then d square V by dx square is equal to minus k at x is equal to 0. So that x is equal to 0 is the unstable point. Then d square v by dx square equal to 2k at x naught is equal to square root over k by lambda. So that x naught is equal to square root over k by lambda is a stable equilibrium point. Then omega is equal to square root over dou square v by dou x square at x is equal to x naught by m, that is equal to square root over 2k by m. Then f is equal to 1 by 2 pi square root over 2k by m. So the next question is, a solid cylinder of height h, radius r and density rho floats vertically on the surface of a liquid of density rho naught. The cylinder will be set into oscillatory motion when a small instantaneous downward force is applied. The frequency of the oscillation is dash. Here we have given that the cylinder is immersed in a vessel. The cylinder having the height h, but only small h is immersed in the liquid, and liquid having the density rho naught and the cylinder having the density rho. And by Archimedes principle we know that the weight of the cylinder is acting downwards, which is equal to water displaced from the beaker. So that Ah into rho g is equal to A small h into rho naught g, that is h rho is equal to small h rho naught. Suppose we consider that the cylinder is immersed more into the water at a distance x, so that F, which is the bound force, that is equal to A capital H rho g minus A into h plus x into rho naught g. This is equal to AH rho naught g minus AH rho naught g minus AX rho naught g. And here we know that F is equal to MA, that is MA is equal to minus AX rho naught g, and AH rho naught g get cancelled, so that A is equal to minus A rho naught g x by m. And we know that omega is equal to square root over A rho naught g by m, because we know that A is equal to minus omega square x, so that omega is equal to square root over A rho naught g by m, that is omega is equal to square root over A rho naught g by A h rho, and this is equal to square root over rho naught g by h rho. This is the answer. The next question is, a solid vertical rod of length L and cross section A is made of a material of Young's modulus Y. The rod is loaded with a mass capital M and as a result extends by a small amount delta L in the equilibrium condition. The mass is then suddenly reduced to M by 2. As a result, the rod will undergo longitudinal oscillation with an angular frequency dash. We know that the Young's modulus is
equal to stress by strain, that is F by A divided by delta L by L, that is Y is equal to FL by A delta L. So from here F is equal to YA delta L by L, and we know that F is mg. So equating these two, we get mg is equal to YA delta L by L. And here it is mentioned that if the m is changed to m by 2, so that F is equal to m by 2 into g. So here the force is m by 2 g. So here the as the mass is changed, this the effect of change of mass should be reflected in the opposite side also, so that here the m is changed to m by 2, so that we know that the left hand side YA by L is constant, so that to make the, if the m is changed to m by 2, to reflect that change, the right hand side should be changed to delta L by 2, so that so that the change in the mass is reflected in the right hand side also. So the force required to bring back the m by 2 to m is delta F, which is equal to YA by L into delta L by 2 minus YA delta L by L. This is equal to minus YA delta L by 2L. So here the force is acting on m by 2, so that F is equal to m by 2A. So equating these two, we get m by 2A, which is equal to minus YA by 2L into delta L. That is A is equal to minus YA by ML into delta L. That is, we know that A is equal to minus omega square x, where x is the displacement, that here the x is delta L. So here omega is equal to square root over YA by ML. The next question is, the time period of a simple pendulum under the influence of the acceleration due to gravity g is t. The bob is subjected to an additional acceleration of magnitude square root over 3g in the horizontal direction. Assuming small oscillation, the mean position and the time period of the oscillation respectively of the bob will be dash. So here there is a bob of mass m, and it making the angle, let's say theta naught, and we know that the bob is having a acceleration due to gravity in the downward direction, that is g, and here it is mentioned that there is also a one more acceleration due to gravity in the horizontal direction, that is square root over 3g. And here a tension force is acting along the length of the bob L, that is T dash. Making it to components, we can write T dash cos theta naught and T dash sin theta naught. And from this figure we can write T dash sin theta naught equal to root 3 mg. This is equation number 1. And T dash cos theta 0 is equal to mg. This is equation number 2. Dividing these two equations, we get tan theta 0 is equal to root 3. That is theta 0 is equal to 60 degree. So the angle is 60 degree. So if we enlarge this picture, we can make it more clear by writing the components. That is, we know that the force that is acting downwards is mg. So if we split it into components, we can write it as mg sin theta and mg cos theta. And here the tension force acting is, let's say T1 dash, and T1 dash is equal to mg cos theta. So here mg sin theta is the restoring force, so it is coming back to the original position, so that the displacement is in the negative direction. So we can say that F is minus mg sin theta, so that the here the negative comes, and we know that F is equal to ma, so that F is equal to minus mg sin theta. This is equal to ma. So here sin theta is approximately equal to theta, that is A is equal to minus g theta, and theta is equal to x by L, that is A is equal to g into x by L, and time period t is equal to 2 pi square root over L by g. Here there is 2g, that is one acting downwards, that is the g, and one acting horizontal, that is root 3g. So that we need to find g dash instead of g to find the time period, that is g dash is equal to square root over g square plus root 3 g whole square, that is equal to 2g. So the time period is 2 pi square root over L by g dash, that is equal to 2 pi square root over L by 2g. This is equal to 1 by root 2 into 2 pi into square root over L by g. This is equal to t by root 2, because we know that t is equal to 2 pi square root over L by g. Here we have taken the resultant value of the acceleration due to gravity, so that we get new time period. So that new time period is t by root 2. So the option here is C, that is the angle is 60 degree and the time period is t by root 2. The next question is, the three particles of equal mass are connected by two identical massless springs of stiffness constants as shown in the figure. If x1, x2, x3 denote the horizontal displacement of the masses from their respective equilibrium positions, the potential energy of the system is dash. Here there are three particles. Let the original position of the particles be x01, x02 and x03. So if we are given a force, so that the position changes to x1, x2 and x3. So here the potential energy is equal to the potential energy of the first spring plus the potential energy of the second spring, and this is equal to 1 by 2 into k into x2 minus x1 minus x02 minus x01 the whole square plus 1 by 2 into k into x3 minus x2 minus x03 minus x02 the whole square, which is equal to 1 by 2 into k into x2 minus x02 minus x1 minus x01 the whole square plus 1 by 2 into k into x3 minus x03 minus x2 minus x02 the whole square. This is equal to 1 by 2 into k into eta 2 minus eta 1 the whole square plus 1 by 2 into k into eta 3 minus eta 2 the whole square, because we know that eta 2 is equal to x2 minus x02 and eta 1 is x1 minus x01. So that this can be written as, by expanding we can write it as 1 by 2 k into eta 2 square plus eta 1 square minus 2 eta 2 eta 1 plus half k into eta 3 square plus eta 2 square minus 2 eta 3 eta 2, which is equal to half k into 2 eta 2 square plus eta 1 square plus eta 3 square minus 2 eta 2 eta 1 plus eta 3. So this is the answer. Next question is, the Lagrangian of a system is given by L is equal to half m q1 dot square plus 2m q2 dot square minus k into 5 by 4 q1 square plus 2 q2 square minus 2 q1 q2, where m and k are positive constants. The frequency of its normal modes are dash. So here L is equal to half m q1 dot square plus 2 m q2 dot square minus k into 5 by 4 q1 square plus 2 q2 square minus 2 q1 q2. So from here we can write T is equal to half into m q1 dot square plus 4 m q2 dot square, and V is equal to k by 2 into 10 by 4 q1 square plus 4 q2 square minus 4 q1 q2. This is equal to k by 2 into 10 by 4 into q1 square plus 4 q2 square minus 2 q1 q2 minus 2 q2 q1. So ignoring the half which is in the outside and writing the matrix, we can write T as m0 0 4m and V as 10 k by 4 minus 2k minus 2k and 4k. Here the matrix of T is written in the form dou square T by dou q1 dot dou q2 dot, and from here we can find each term in the matrix of T. And for V, the matrix is written by dou square V by dou q1 dou q2. So from here we can also write each term in the V matrix.
Then we know that v minus omega square t is equal to 0. That is matrix of 10k by 4 minus 2k minus 2k 4k minus omega square into m0 0 4m is equal to 0. That is 10k by 4 minus omega square m minus 2k minus 2k 4k minus omega square into 4m is equal to 0. That is 10k by 4 minus omega square m into 4k minus omega square into 4m minus 4k square is equal to 0. That is 10k square minus 10 by 4 into k into omega square into 4m minus 4k omega square m plus omega raised to 4 into 4m square minus 4k square is equal to 0. That is 10k square minus 10k omega square m minus 4k omega square m plus 4 omega raised to 4 m square minus 4k square is equal to 0. That is 6k square minus 14k omega square m plus 4m square omega raised to 4 is equal to 0. That is 3k square minus 7k omega square m plus 2m square omega raised to 4 is equal to 0. And this can be written as 3k square minus omega square km minus 6 omega square km plus 2 omega raised to 4m square is equal to 0. That is minus 2 omega square m into 3k minus omega square m into k into 3k minus omega square m is equal to 0. That is 3k minus omega square m into k minus 2 omega square m is equal to 0. Then k minus 2 omega square m is equal to 0 means k minus k is equal to 2 omega square m. That is omega is equal to square root over k by 2m. Then 3k minus omega square m is equal to 0. That is 3k is equal to omega square m. Then omega is equal to square root over 3k by m. That is here the omega values are omega is equal to square root over k by 2m and omega is equal to square root over 3k by m. So the next question is a particle moves in the one-dimensional potential V is equal to A x raised to 6, A greater than 0 as a constant, and if the total energy of the particle is E, its time period in a periodic potential is proportional to dash. And here V is equal to A x raised to 6, E is equal to P square by 2m plus A x raised to 6. That is E minus A x raised to 6 is equal to P square by 2m. Then P is equal to plus or minus square root over 2m into E minus A x raised to 6. So in this equation, if P is equal to 0, E is equal to A x raised to 6. That is x is equal to E by A the whole raised to 1 by 6. So J is equal to integral over P dx. That is equal to 4 into integral over 0 to E by A the whole raised to 1 by 6 into square root over 2m into E minus A x raised to 6 into dx. This is equal to 4 into square root over 2me integral over 0 to e by a the whole raised to 1 by 6 into square root over 1 minus a x raised to 6 by e into dx. And if we put a by e into x raised to 1 by 6 is equal to t, dx is equal to e by a the whole raised to 1 by 6 into dt. So the j can be rewritten as j is equal to 4 into square root over 2me into integral over 0 to e by a the whole raised to 1 by 6 into square root over 1 minus t raised to 6 into e by a the whole raised to 1 by 6 into dt. This is equal to 4 into square root over 2me into e by a the whole raised to 1 by 6 into integral over 0 to e by a the whole raised to 1 by 6 into square root over 1 minus t power 6 into dt. So taking all these constants outside and write it as x naught, we can write j as x naught into e raised to 1 by 2 into e raised to 1 by 6. That is equal to x naught into e raised to 2 by 3. Then time period t is equal to dou j by dou e. This is equal to 2 by 3 into x naught into e raised to 2 by 3 minus 1. This is equal to 2 by 3 into x naught e raised to minus 1 by 3. That is t is proportional to e raised to minus 1 by 3. The next question is a particle of mass m moves in one dimension in the potential V is equal to k x raised to 4. At the time t is equal to 0, the particle starts from rest at x is equal to a. For bounded motion, the time period of this motion is dash. So here E is equal to p square by 2m plus k x raised to 4. Then if
p is equal to 0, e is equal to k x raised to 4, then x is equal to e by k the whole raised to 1 by 4. And from this equation we can write p is equal to plus or minus square root over 2m into e minus k x raised to 4. And we know that j is equal to integral over p dx, that is equal to 4 into integral over 0 to e by k the whole raised to 1 by 4 into square root over 2m into e minus k x raised to 4 into dx, that is equal to 4 into square root over 2me into integral of 0 to e by k the whole raised to 1 by 4 into square root over 1 minus k x raised to 4 by e into dx. This is equal to e by k the whole raised to 1 by 4 into 4 into root of 2me into integral of 0 to 1 into square root over 1 minus t raised to 4, because we know that k by e the whole raised to 1 by 4 into x is equal to t, and dx is equal to e by k the whole raised to 1 by 4 into dt. The limit is changing to 0 to 1 with respect to this substitution, and this or taking all these constant outside and can write it as x naught, so the j value will changes to x naught into e raised to 1 by 2 into e raised to 1 by 4, so that j is equal to x naught e raised to 3 by 4. Then t is equal to dou j by dou e, that is equal to x naught 3 by 4 into e raised to 3 by 4 minus 1, that is 3 by 4 x naught e raised to minus 1 by 4. So t is proportional to e raised to minus 1 by 4. And at extreme position we know that kinetic energy is 0, and let that position be x is equal to a, and then energy will be equal to k x raised to 4, this is equal to k a raised to 4. That means we know that time period t is proportional to e raised to minus 1 by 4, and we know k is equal to e is equal to k a raised to 4, so that t proportional to k a raised to 4 the whole raised to minus 1 by 4, that is t proportional to a raised to minus 1. So t is proportional to a raised to minus 1 is the answer. The next question is the energy of a one-dimensional system governed by the Lagrangian L is equal to half mx dot square minus half k x raised to 2n, where k and n are two positive constant as E naught. The time period of oscillation tau satisfies. Here Lagrangian L is equal to half mx dot square minus half k x raised to 2n. P is equal to dou L by dou x naught dot, that is equal to half into 2m x dot, that is equal to mx dot, that is p is equal to mx dot, that is p x dot is equal to p by m. Then h is equal to x dot p minus l, that is x dot p minus half mx dot square plus half k x raised to 2n, that is p square by m minus half m p square by m square plus half k x raised to 2n, because we have substituted the value of x dot here, and this is equal to p square by m minus half p square by m plus half k x raised to 2n, that is half p square by m plus half k x power 2n. Then e is equal to p square by 2m plus half k x raised to 2n, then p is equal to plus or minus square root over 2m into e minus half k x power 2n. Then j is equal to integral over p dx, that is equal to 4 into integral over 0 to 2e by k the whole raised to 1 power 2n, because in the p is equal to plus or minus square root over 2m into e minus half k x power 2n, if we put p is equal to 0, then e is equal to half k x power 2n, then 2e by k the whole raised to 1 by 2n become x. So the limit changes from 0 to 2e by k the whole raised to 1 by 2n, that is j is equal to 4 into integral of 0 to 2e by k the whole raised to 1 by 2n plus or minus square root over 2m into e minus half k x power 2n into dx, that is equal to 4 into root 2me integral over 0 to 2e by k the whole raised to 1 by 2n square root over 1 minus k x power 2n by 2e into dx. Here we substitute k by 2e the whole raised to 1 by 2n into x is equal to t, that is equal to dt is equal to 2e by k the whole raised to 1 by 2n. Substituting all these values in this equation, we can write it as 4 into root 2me into 2e by k the whole raised to 1 by 2n into integral over 0 to 1 into square root over 1 minus t power 2n into dx. Taking all the constants outside and write it as x naught, we can write j as equal to x naught by k raised to 1 by 2n into e raised to 1 by 2n into e raised to 1 by 2, that is equal to x naught by k raised to 1 by 2n into e raised to 1 by 2n plus 1 by 2. Then T, that is tau is equal to tau j by dou e, that is equal to 1 by 2n plus 1 by 2 into x naught into e raised to 1 by 2n plus 1 by 2 minus 1 into 1 by k raised to 1 by 2n. And this is equal to 1 plus n by 2n into e raised to 1 plus n by 2n minus 1 into 1 by k raised to 1 by 2n. This is equal to 1 plus n by 2n into e raised to 1 minus n by 2n into k raised to minus 1 by 2n. That is, t is proportional to e raised to 1 minus n by 2n into k raised to minus 1 by 2n. So this is the answer. The next question is the time period of a particle of mass m undergoing small oscillation around x is equal to 0 and the potential V is equal to V naught cos h x by L is dash. Here V is equal to V naught cos h x by L, then dou V by dou x is equal to 0, that is V naught by L into sin h x by L is equal to 0, that is sin h x by L is equal to 0, that is x by L is equal to 0, that is x is equal to 0. Dou square V by dou x square at x is equal to 0 is equal to V naught by L into 1 by L into cos h into x by L, that is equal to V naught by L square. This is positive, this is the stable equilibrium point. And we know omega is equal to square root over k by m. This is equal to square root over v naught by m l square. Then t is equal to 2 pi by omega, that is equal to 2 pi into square root over m l square by v naught. So the next question is, consider a particle of mass m attached to two identical springs, each of length L and spring constant K. The equilibrium configuration is the one where the springs are unstretched. There are no other external force on the system. If the particle is given a small displacement along this x-axis, which of the following describes the equation of motion for small oscillation? So here two springs are given. Let the position of the mass be the origin, that is 0 0. So the first spring, that is S1, is having the length L. Then the topmost point is having the coordinate 0 comma L, and below it the length is minus L, so that the point is 0 minus L. That is, the S1 support have the coordinate 0 comma L and S2 as the coordinate 0 comma minus L. So the coordinate of the particle be x comma 0. So the length of the upper string L1 is equal to square root over x minus 0 the whole square plus 0 minus L the whole square. This is equal to square root over x square plus L square. Then the length of the lower string L2 is equal to square root over x minus 0 the whole square plus 0 minus L the whole square. That is equal to square root over x square plus L square. And here L1 is equal to delta L plus small l. Then delta L is equal to L1 minus L, and this is also equal to L2 minus L, and this is equal to square root over x square plus L square minus L. And here V is equal to half k delta L the whole square plus half k delta L the whole square, and this is equal to k delta L the whole square. This is equal to k into square root over x square plus L square minus L the whole square. Square root over x square plus L square is equal to L into square root over 1 plus x square by L square. This is equal to L into 1 plus x square by L square the whole raised to 1 by 2. That is equal to L into 1 plus half into x square by L square. That is, delta L is equal to square root over x square plus L square minus L. This is equal to L by 2 into x square by L square. This is equal to x square by 2L. Then V is equal to k into x raised to 4 by 4L square, that is equal to k x raised to 4 by 4L square. Then L is equal to half m x dot square minus k x raised to 4 by 4L square. Then d by dt of dou L by dou x dot minus dou L by dou x is equal to 0. This is the equation of motion. So that d by dt of mx dot plus k by 4L square into 4x raised to 3 is equal to 0. That is mx double dot plus k x raised to 3 by L square is equal to 0. So this is the equation of motion in this question. So the next question is, two particles of masses m1 m2 are connected by a massless thread of length L as shown in the figure below.
The particle of mass in on the plane undergoes a circular motion with radius r0 and length L. When a small radial displacement epsilon is applied, its radial coordinate is found to oscillate about r0. So the frequency of the oscillation is dash. So here it is asking about the frequency. So here in this plane there is a mass m1 having the radius r0, and in the downward direction there is a mass m2 and is having the length l minus r. Here the potential is 0 in the reference that is passing through the center of the point present in the table. So here we have said that L minus R, and we have taken L minus R as x2, that is x2 dot is equal to minus R dot. So in polar coordinates t is equal to half m1 r dot square plus r square theta dot square plus half m 2 into x2 dot square, that is minus r dot square. So this is equal to half into m1 plus m2 into r dot square plus half into m1 r square theta dot square. Then here v is minus m2g into L by R. Here potential energy is negative because here the m2 is below the reference frame. So here the reference is taken as potential energy is 0. So that below that reference the potential is negative, so that V is negative here for m2. So that V is equal to minus m2g into L minus R. Then Lagrangian L is equal to half m1 plus m2 into r dot square plus half m1 r square theta dot square plus m2g into L minus R. D by dt of dou L by dou R dot minus dou L by dou R is equal to 0, because here R is the generalized coordinate. Then d by dt of half into m1 plus m2 into 2R dot minus half into m1 theta dot square into R plus m2g, that is half into m1 plus m2 into 2R double dot minus m1 theta dot square into R plus m2g, that is m1 plus m2 into r double dot minus m2 r theta dot square plus m2g is equal to 0. This is equation number 1. And we can also write the equation of motion in terms of theta, because theta is also a generalized coordinate here, that is d by dt of dou L by dou theta dot minus dou L by dou theta is equal to 0. So that d by dt of m1 r square theta dot is equal to 0, that is m1 r square theta dot is equal to a constant. This is equation number 2. At r equal to r naught, theta dot is equal to omega, that is r double dot is equal to 0, because r is a fixed quantity, so that r double dot is equal to 0. And if we substitute theta dot is equal to omega in equation number 2, we can write it as m1 r0 square omega is equal to m1 r square theta dot, that is omega is equal to r square theta dot divided by r0 square. Then equation 1 implies m2g minus m1 r0 theta dot square is equal to 0, that is m2g minus m1 r0 omega square is equal to 0, that is m2g by m1 r0 is equal to omega square, that is m2g by m1 r0 is equal to r raised to 4 theta dot square by r0 power 4. So m2g by m1 is equal to r raised to 4 theta dot square by r0 raised to 3, that is theta dot square is equal to r0 raised to 3 m2g by r raised to 4 by, into m1, that is equation number 3. Substituting the value of 3 in 1, we get m1 plus m2 into r double dot plus m2g into 1 minus r0 raised to 3 by r raised to 3 is equal to 0. And if a small displacement is given in such a way that r is equal to r0 plus epsilon, that is dot is equal to a constant plus epsilon dot, that is r double dot is equal to epsilon double dot, that is
m1 plus m2 into epsilon double dot plus m2g into 1 minus r0 raised to 3 plus r0 plus epsilon the whole raised to 3, which is equal to 0. That is m1 plus m2 into epsilon double dot plus m2g into 1 minus r0 raised to 3 divided by r0 raised to 3 into 1 plus epsilon by r0 the whole raised to 3. This is equal to 0. And this is m1 plus m2 into epsilon double dot plus m2g into 1 minus 1 plus epsilon by r0 the whole raised to minus 3. Here epsilon less than r0, so we can see we can use the binomial expression, that is m1 plus m2 into epsilon double dot plus m2g into 1 minus 1 plus 3 epsilon by r0 is equal to 0. That is m1 plus m2 into epsilon double dot plus m2g into 3 epsilon by r0, this is equal to 0. Dividing by m1 plus m2, we get epsilon double dot plus 3 m2g epsilon by r0 into m1 plus m2 is equal to 0. So the equation is in the form of x double dot plus omega square x is equal to 0. That is omega square is equal to 3 m2g divided by r0 into m1 plus m2. So that omega is equal to square root over 3 m2g divided by m1 plus m2 into r0. So this is the answer. The next question is, the spring constant K of a spring of mass ms is determined experimentally by loading the spring with mass capital M and recording the time period t for a single oscillation. If the experiment is carried out for different masses, then the graph that correctly represents the result is dash. And here the spring is having the length L. So here if we consider a infinitesimal length, and that length is dt, which is at a distance of t from the top point. That is, the velocity in the length dt at a distance t can be written as x dot minus 0 by L into t. This is because at the starting point, that is at the topmost point, the velocity is 0, and at the bottom point velocity is x naught, so that it is written as the velocity in the length dt at a distance t is written as x dot minus 0 by L into small t. The kinetic energy of the spring is dk1, that is dk1 is equal to half into msv square, that is equal to half into ms by L into dt into x dot t by L the whole square, that is equal to half into ms x dot by L cube into integral over 0 to L into t square dt, that is equal to half into ms x dot square by L raised to 3 into L raised to 3 by 3, that is equal to 1 by 6 into ms x dot square. Then the kinetic energy of the mass capital M is equal to half capital M x dot square, that is T is equal to 1 by 6 into ms x dot square plus half m x dot square, that is equal to half into m plus ms by 3 into x dot square. So this is T, and here V is equal to half k x square minus mgl minus mgl by 2. Here mgl by 2 is the gravitational potential term, and here Lagrangian L is equal to half into m plus ms by 3 into x dot square minus half k x square plus mgl plus mgl by 2. And the equation of motion is d by dt of dou L by dou x dot minus dou L by dou x is equal to 0. That is m plus ms by 3 into x into x double dot minus kx is equal to 0. That is x double dot plus k by m plus ms by 3 into x is equal to 0. So omega is equal to square root over k by m plus ms by 3. Then t is equal to 2 pi by omega, that is 2 pi into m plus ms by 3 by k, that is t square is equal to 4 pi square into m plus ms by 3 by k, that is equal to 4 pi square m by k plus 4 pi square ms by 3k, that is t square is proportional to m with the additional term 4 pi square ms by 3k. So here this shows that the graph is a straight line.
So this is the end of this video. Thanks for watching this channel.